All right, today we're going to talk about area. So, but before that, we're going to talk about summation notation again, which is a review from what we did in pre-calculus. But there's a lot of this involved, so you're going to want to make sure that you know this stuff pretty good. So the sum of n terms, a sub 1 plus a sub 2 plus a sub 3 plus up to a sub n, is written as the sum from I equals 1 to n of the a sub i's, which really means a sub 1 plus a sub 2 plus a sub 3 plus up to a sub n. Where I is the index of the summation, so the I, remember, is just the number. This is the first term, the second term, the third term, the nth term of a sequence. And the upper and lower bounds of the summation are n and 1. So you're going to count from 1 to n, whatever n is in this case. This could be, and you can do this with a variable, you can do it with a finite end, or you can do it with an infinite upper bound. Okay, so some examples here. So the sum from I equals 1 to 6 of the i's, that's just 1 plus 2 plus 3 plus 4 plus 5 plus 6. That's all it is. So the I is becoming 1, and then it's 2, and then it's 3, and you're just adding those numbers up. So here the sum from I equals 0 to 5 of I plus 1, this is the same thing as this is, because I plug the 0 in here and I start out at 1, and I get all the same numbers, and then I plug the 5 in and I get 6. So that ends up being the same thing. The sum from j equals 3 to 7 of the j squareds means 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Okay, pretty much you can look at these. You know, they're really similar. This is the one you really want to look at because we're going to see this quite a bit in this lesson. The sum from I equals 1 to n of the f of x sub i's times delta x's. Okay, so this is just f of x sub 1 times delta x plus f of x sub 2 times delta x plus dot 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 plus f of x sub n delta x. Remember, delta x means change in x, and that's going to come in very prominently today, this formula. Okay, so some properties of summation. So the sum from k equals 1 to, or I equals 1 to n of the k times a sub i's is equal to k times the sum from I equals 1 to n of just the a sub i's. So basically what that means is if I have a constant in here, I can take the constant out. So if I was going to do, say, the sum from I equals 1 to 10 of the 3 i's, well, I can just take the 3 outside, find the sum from I equals 1 to 10 of the i's, and then just multiply that times 3, and that gives me the answer. Okay. Here, the sum from I equals 1 to n of the a sub I plus b sub i's, or it could be minus, you can break that apart into two pieces. So this would be something like this. The sum from I equals 1 to, say, 20 of, sorry, I'm usually used to using k's here, but I squared plus i's, okay? So what I can do is I can just break this up and make this the sum is I equals 1 to 20 of the I squareds plus the sum from I equals 1 to 20 of the i's. And then I can find this and I can find that. I can add the answers together, and that gives me the answer to this. Now that's really cool to have these two properties because I don't have to memorize a whole bunch of different formulas. I only need to know a few, and then I can use their properties to get the other answers that I want. So some summation formulas you definitely want to know. The sum from I equals 1 to n of the c's is c times n, where c is a constant. Okay, this would be something like the sum from I equals 1 to 20 of the 4's. Okay, that just means 4 plus 4 plus 4, 20 times. So this is just 4 times 20, which is 80. And you're done. You can do that with any constant. Next, the sum from I equals 1 to n of the i's is n times n plus 1 over 2. So this would be something like this. The sum from I equals 1 to 7 of the i's is just going to be 7 times 8 divided by 2, which is 56 divided by 2, which is 28. You can verify that by just adding up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, and you're going to get 28. Okay, next. This is the formula that people always have a hard time remembering. The sum from I equals 1 to n of the I squareds is just n times n plus 1 times 2n plus 1 divided by 6. So what that means is, let's say I have the sum from I equals 1 to 9 of the I squareds. So this would be 9 times 10 times 19 divided by 6. So that's easily done on a calculator. Comes out to be 285. You don't have to add up 9 different numbers and square 9 different numbers and all that kind of stuff. Okay, and then lastly here, I equals the sum from 1 to n of the I cubes. That's just n squared times n plus 1 squared divided by 4. Now, I don't usually use that formula. I prefer this one. It's n times n plus 1 divided by 2 squared. And the reason I like that one is because it's exactly like this one, except I square it. Okay, so it's easier to remember that way. And then there's formulas for I to the 4th and I to the 5th and I to the 6th too, but we hardly ever use those. So anyway, let's move along. So here we're going to evaluate the sum from I equals 1 to n of the I plus 1 over n squareds for 10, 100, 1,000, 10,000. Well, I'm only going to do one of these. I'm going to do 10. You can do the other ones on your own. Okay, so this would be, since n is going to be a constant in this thing, I can factor out the 1 over n squared, and then I'm left with, I'm not sure what happened there. Let's try this again. So I can take the sum from I equals 1 to n, and I can factor out the 1 over n squared, and that just leaves me with I plus 1 like this, which I can break up into two different things. Oops, and this is to 10 because we said we were going to do it to 10. So this would be 1/100th down here. Okay, and so that makes this 1/100th, sum from I equals 1 to 10 of the i's plus the sum from 1 to 10 of the 1's. Okay, so then this is equal to 1 over 100 times, okay, this is the sum of the i's, so this is going to be 10 times 11 divided by 2 plus 10 times 1. Okay, so this is 110 divided by 2, that's 55. So this is 1 over 100 times 55 plus 10, which is 1 over 100 times 65, which is 0.65. And pretty much the only difference would be is if I do this to 100 or 1,000 or 10,000, I'm going to change this number, I'm going to change this number, and that's it. So that's going to change the formulas, obviously, but by breaking it up like this, it allows me to do the formulas easily. I can do it in my head, actually. Okay, area of a plane region. So here's the way you approximate the area. So when you were in geometry, you did area formulas of squares and rectangles and triangles and parallelograms and circles and trapezoids, that type of stuff. Pretty easy formulas. But what do you do when you have a curve? Okay, so one of the ways that you can do this is, so we've got an example here. We've got f of x is negative x squared plus 5. Okay, what you can do is you can take the interval. So we want the area under the curve above the x-axis, okay? So basically we want the area that is that's inside this red shape right here, okay? So what we can do is we divide that area up into even spaces, okay? And, you know, we talked about delta x before. This distance right here, this is what your delta x is. And then we can fit these rectangles underneath here like this. Okay, now rectangle, you can find the area by base times height. Okay, so this point right here, that's the height of this rectangle. Okay, that's this side right here. So this is f of x, well, this would be f of x2 in this case. Okay, f of x1 would be, oh wait, sorry, we're doing the right side, so this would be f of x1. Okay, this would be f of x2, f of x3, f of x4, and f of x5. Okay, so what we do is we find the area of these rectangles and just add them up. So this becomes the sum as I equals 1 to 5 in this case, because we have 5 partitions here, okay, of the f of xi's times delta x's. So this is your base times your height, and we do that for the 5 different sections, and we get an approximate area. Now this has an error, okay, because this stuff right here is not included in that, and so we're actually short some of the area that we need. Okay, so what we can do is on this one we use the right corner. We could do the left corner on this side here and use this. So this is now x sub 1, this is x sub 2, x sub 3, x sub 4, x sub 5. Okay, and we can do the same thing as this. Now this one is going to be too big because I'm going to have the area here, 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 and here that is not included. Okay, and so, and this also. This is also not included. So I have some error in this. But what I could do is I could take this and average those, and I'm going to be really close to the area of this under this curve. Okay. All right. So the only difference is this is x1, x2, x3, x4, and x5 over here. And they're all just shifted 1 over in each case. Okay, so I find the area of those rectangles, I add them up. I find the area of these rectangles, I add them up. I average that, and I can get a very close approximation to the area underneath this curve. Okay, so upper and lower sums. So that's pretty much what I just did on the other page here. So consider a plane region bounded by the graph of a non-negative continuous function y equals f of x. So I've got this nice curve right here. Okay, this is some kind of cubic probably, okay, right here. And I want the area above the x-axis under that curve between A and B. Now you don't have a formula for this kind of shape, okay? So we have to use calculus to find this area. Okay, so we're going to divide this thing into intervals, into small intervals. And the base of these, and it's going to form rectangles. So the base of that rectangle is called delta x. And the way you find that is very simple. You take b, which is right here, and you subtract a, and then you divide that by the number of intervals that you have. So if you have 2 intervals, you're not going to be very accurate. If you have 25 intervals, it's going to be much more accurate. The more intervals you divide this into, the thinner these rectangles are, the closer and closer you get to the actual area underneath this curve under here. Okay, so delta x is b minus a over n. Super simple to figure out. Okay, that gives you the base. Now the height's sometimes a little bit more difficult. Okay, because here's a point C right here. Okay, and then this is f of c. That's the height. So whatever corner of this rectangle is on the curve, that's what you want to use for your f of c. Okay, and then there's your height, and there's your base, and you multiply that, find the area of the rectangles, and you add up all the rectangles. So you can do the lower sum right here. So this one, it's always inscribed in the shape. Or you can do the upper sum, which this one's always circumscribed around the shape. And then you can average those, and that's going to give you actually what you get underneath that curve. That's going to give you the area of that region. And it's not going to be exact if you average them, but there are techniques that we'll have for finding the exact areas. Okay. So find the upper and lower sums for the region bounded by the graph of f of x equals x squared and the x-axis between 0 and 2. So here's what I'm doing is I'm finding the area from 0 under this curve right here from 0 to 2. So here's 2. Find the area of that shape right there. That was all the same. Okay, a little thinner so you can see better. Okay, so this one's inscribed, and you'll notice we use in the left corner of this thing. So here's my f of x1, or here's my f of x1, f of x2, f of x3, f of x4, f of x5. So I've divided this thing into 5 sections. Okay, and so what that tells me is that delta x is going to be 2 minus 0 divided by 5, because I divided it into 5 pieces. And don't forget, there's a piece right here that on this is actually 0 in height, so you got to include that one. So delta x is 2/5. Okay, and it's the same for this one over here. Delta x is also 2/5. I'm just using the right corner instead of the left corner on each of these. Okay, so then the sum from I equals 1 to 5, because they have 5 sections, of f of ci delta x, okay, the delta x is going to be 2/5, okay, and the first one right here is going to be 0, okay, because I'm going to plug 0 into x squared. Remember, my formula, my f of x is x squared here, so this first one is going to be 0 times 2/5 plus, now I go to the second one, which is right here, and the height of that is going to be 2/5 squared, because I'm going to plug, this is 2/5 right here, I'm going to plug it in, x squared, times the base is 2/5 plus, the next one is going to be 4/5 squared times 2/5 plus 6/5 squared times 2/5. Let's see, that's 1, 2, 3, 4. I got one more, so the next one's going to be 8/5 squared times 2/5. Okay, now if you're wondering where I got these numbers, okay, remember I took 2 minus 0 and divided that by 5, so I have 5 sections. So if I count the bottom here, this is 0, this is 2/5, this is 4/5, this is 6/5, this is 8/5. Okay, over here, since we're using the right side, this one would be 2/5, 4/5, 6/5, 8/5, and 10/5, which is just 2. Okay, so now I can calculate what this is. So this is 0, okay, so then 2/5 0.4 squared times 0.4 plus 0.8 squared times 0.4 plus 6/5. That's 1.2 squared times 0.4 plus 8/5 is 1.6 squared times 0.4. Boom, 1.92. Approximate. I should have an approximate sign here. Okay, now this is smaller than the actual area of this because I'm missing all this spot here. Okay? Now, if I did this other one here, I'm going to get exactly the same numbers here, except my first one is not going to be this, it's going to be this one, and my last one is going to be plus 2 squared times 2/5. So I can actually take this, and I don't have to rework the wheel here, plus, 2 squared, so that's 4, times 0.4. And it comes out to be, if I do this one, this is 3.52 approximately. Now this is too big because I've got all these areas right here that are not under the curve. Okay, so I can average those two things, divide that by 2, and I'm going to get about 2.72, and that's going to be about my area underneath that curve. It's going to be pretty close. Okay? All right, so limits of lowers and upper sums. So let f be continuous and non-negative on the interval AB. The limits as n goes to infinity of both the lower and the upper sum exist and are equal to each other. So basically what this says is the limit of the sum of the n's is equal to the limit as x goes to infinity of the sum of the f of little mi's delta x, which is equal to the limit as x goes to infinity of the sum of f of big mi delta x. So what that is here's my little m's over here, here's my big m's over here. And so what they're saying is if I make these rectangles smaller and smaller and smaller because I make more and more intervals in here, the area that I get with this and the area I get with this get closer and closer together until they're equal. Okay? And that is just this right here. Okay? Where delta x is b minus a divided by n. So this is just your ending point, subtract your beginning point, divided by the number of intervals you want to have. And these are the minimum values, and those are the maximum values of f on the subinterval. Okay, now you can also do this kind of thing where instead of using the left corner or the right corner, you can use the midpoint of the corner, or the midpoint of the rectangle. Okay, and that's going to leave you with a little bit of error right here that's under the curve and a little bit of error right here that's over the curve, and so they kind of cancel each other out, and you get pretty close to the actual area under that one as well. Okay. All right, so finding area by the limit definition. Okay, so this is kind of tough for people sometimes. It's really not that hard, but it's really easy to get confused with. So here we go. So we're going to find the area of the region that's bounded by the graph of f of x equals x cubed. So here's my x cubed. Okay. And we're going to find that between 1 right here and 0 right here and above the x-axis. So we're going to find the area right there. Okay. So the first thing that we're going to do, the area is going to be the limit as n goes to infinity of the sum of from I to n of the f of c sub i's times delta x's. Okay, so basically what this says is I'm going to take the base, that's the width of that rectangle, times the height. Here's f of c, so here's c down here, here's f of c, it's on the curve. Okay, I'm going to take all those rectangles and I'm going to add them up from 1 to n. So I'm going to divide this into n intervals. And then I'm going to take the limit as n goes to infinity. So what that means is those rectangles are going to shrink in width and get closer and closer and closer to just a segment. Okay? And when they become a segment, that's when I'm going to actually get the actual answer to my area. Okay, so what is this? So delta x is going to be 1 over n because I'm using n intervals and I'm going between 1 and 0. So I take 1 minus 0 is 1, and I divide that by the n intervals, and so that's my delta x right there. Now, since that's my delta x, and I'm starting at 0, okay, or I'm starting at, I'm not actually starting at 0, I'm starting at 1 over n, then 2 over n, and 3 over up to n over n, okay? And then this is my f of ci, so my c's are the numbers along here, and then I'm plugging them into x cubed. So this is 1 over n cubed. Okay, so it's 1 over n cubed times 1 over n is 1 over n to the fourth. Whoops, I'm sorry. This is, made a slight mistake here. It's I over n cubed. Okay, so if I take, I can factor out this is 1 over n cubed, okay? Or it's I cubed times 1 over n cubed. So I can take that 1 over n cubed, multiply it by 1 over n. I can take that out because this is going to be a constant. Okay, and I'm left with I cubed on the inside here. Okay, now I find the limit of this. Well, I have a formula for this. Okay, and that formula is n times n plus 1 over 2 squared. Okay, and here's my 1 over n to the fourth, so I know this goes here, and this becomes this. And I take the limit as n goes to infinity. Okay, now if you were following along in the book, they skip a bunch of steps here, which drives me crazy, so I put in a bunch of extra steps that are not in the book. So I distributed the n in here. That's all I did going from here to here. And then I squared this, okay? So took this and FOILed it. Thought I had that over here. Thought I worked that out. Is it over here? Yep, okay, here we go. So for your convenience, n squared, I broke this apart. This is n squared over 2 plus n over 2, and then I squared that. And then that's, I FOILed it, okay? So if you're foiling it, you know, n squared times n squared over 2 times n squared over 2 is n to the fourth over 4. And then you get the outside and the inside. Okay, that's 2 times n squared over 2 times n over 2. And then n over 2 times n over 2. That becomes this. And you combine your like terms in the middle, and you get that. Okay, so this 2 cancels out one of those 2's. Whoa, didn't mean to throw that down there. This 2 cancels one of those 2's, and you're good to go. Okay, so we take this and we substitute it in here. And then we distribute the 1 over n to the fourth in here. Well, that cancels out this n to the fourth and leaves you with 1/4. Okay, it cancels out those 3 and leaves you, and this cancels, leaves you 1 over 2 with an n on the bottom. This cancels those 2, leaving you 2 on the bottom, leaves you with this. Okay, now you can probably do this in your head, because as n goes to infinity, this shrinks to 0, this shrinks to 0, and I'm going to be left with 1/4. Okay, so the area under that curve is going to be 1/4. Now, fortunately, there's an easier way to do this, which I'm going to teach you next class, but you got to learn it today. So, moving on. So here we're going to find the area by the limit definition again. This time we're going to find the area of the graph under f of x equals 4 minus x squared. So that's this curve right here between 1 and 2 and above the x-axis. Okay, so this looks kind of like a line, but it's not really. If you look close, it's actually a curve, and it's going to be an upside-down parabola. Okay? Okay, so we're going to partition the interval into n subintervals. So delta x is going to be 1 over n. Okay? It's going to be 2 minus 1 divided by the number of intervals, which is n, so that's just 1 over n. There was something in between. There we go. Okay. So then C sub I is going to be A times I, or A plus I times delta n, or delta x, which is going to be 1 plus I over n. So what does that mean? Okay, so the C's that I'm going to use, so in this case, a good color to use here, something bright. Okay. If I want these points right here, I need a c sub I right here, and this is my f of c sub I right there. Okay, that gives me the height of the rectangle, and then the delta x is the base of this thing. That's this right here. Okay, so it's going to be 1 plus I over n. So then that gives me the area is going to be the limit as n goes to infinity of the sum from I equals 1 to n of the f of c sub i's times delta x's. So it's just basically the sum of the base times the height of all those rectangles. Okay, so delta x was 1 over n. That was easy because we just took, the distance 1 and divided by n. Okay, the f of c, we're going to substitute the c sub i's into this formula, 4 minus x squared. So this is 4 minus x squared right here. And my first one is going to be 1 minus I over n. And that's going to be squared because it's x squared. And now it's just a bunch of algebra. Once you get this part done, the rest is just algebra. Sometimes hard algebra. Okay, so I square this stuff in here, and I get this. Okay, so you can FOIL that. Oh yeah, I did that over here. Okay, so I minus I over n squared is going to be 1 minus I over n times 1 minus I over n. And then I FOIL that, so 1 times 1 is 1. I get minus 2 I over n's plus I squared over n squared. And I just get this, which I substituted in over here. Okay, so then I get 3 minus 2i. I think this was a plus. Somewhere I got a minus sign wrong here. Hang on a second while I check my work. Okay, yeah, I had this is supposed to be a plus. Right here. So this ends up being a minus and a minus. Oh, yeah. There we go. Okay. You can go back and look at that in just a second. So I distribute my 1 over n inside here, and I get 3 over n, 2i over n squared, I squared over n cubed. And I take the limit of that sum. And I break this thing apart, okay? So I can break this into 3 pieces and find the sum of the 3 pieces. And then I can take the n's. That's going to be a constant. I can take those outside. So I just find the sum, or 1 over n times the sum from I equals 1 to n of the 3's. And then this stuff here times the sum of the i's. And this stuff times the sum of the I squareds. Well, there's formulas for this, this, and this. Okay, so this one's just 3n. This is n times n plus 1 over 2. And this one's n times n plus 1 times 2n plus 1 over 6, which is a little hard to read on that. So I was running out of room. And I distribute my n's back in here, and I get this line right here. And I FOILed this and multiplied by n to get this. I divided the n squareds out of here, and the n cubes, and divided the 2 by the 6 and got a third and a half and a sixth. And then as n goes to infinity, this goes to 0. So this becomes 3 minus 1 minus a third, because these end up being 0, which that comes out to be 5/3. Okay. Sometimes you get a function that's in terms of y, because if you look at this one in terms of x, sometimes you have problems because it ends up not being a function. So you can look at it as in terms of y, and you can just do it sideways, okay? So we're going to find the area between this curve and the y-axis this time. Okay? So we're going to let delta y be 1 over n this time. And the area is going to be the limit as n goes to infinity. That's really hard to see right there. So we're going to make that a little easier to read. The sum of the FCIs times delta y this time. Okay, there we go. So this is y squared this time. So this is going to be, in terms of y, it's going to be I over n. So I'm counting by I over n here. Okay, because it's 1 minus 0 divided by n. So this is 0, and 1 over n, and 2 over n, and 3 over, so on. So, now what I can do is, this is I squared over n squared times 1 over n, so I can take, that's 1 over n cubed, so I can take that out, because that's a constant, and I'm just left with I squared in here, which we have a formula for, n times n plus 1 times 2n plus 1 over 6. And if I multiply that all out, I get this, kind of on your own for that one. And I can divide this out, okay, and I get, and I multiply the 1 over n cubed in here, and it becomes 1/3 plus 1 over 2n plus 1 over 6n squared, which is, if I take the limit as n goes to infinity of that, this is 1/3, this is 0, and that's 0, so it ends up being 1/3. Okay, the midpoint rule. So all this is, here's your delta x just like it was before. That's the base of your rectangle. The height of your rectangle this time is going to be 2 consecutive x's added together and divided by 2. So you're finding the average of 2 consecutive x's and then plugging that into f. Okay, and so there's your formula. And now we've got one here that we can approximate the area with the midpoint rule. Okay, so use the midpoint rule with n equals 4 to approximate the area of a region bounded by the graph of f of x equals sine x, and the x-axis between 0 and pi. Okay, so here's the thing. Let's look at the picture here. Here's 0. Right here, here's pi over here, okay, and it's divided into fourths, so this is pi over 4, pi over 2, 3 pi over 4. Okay, if I want the midpoint of each of those, well, the midpoint of 0 and pi over 4 is going to be pi over 8. And the midpoint between pi over 4 and pi over 2 is going to be 3 pi over 8. It's going to be eighths. This is going to be 5 pi over 8. It's going to be 7 pi over 8. Okay, so now this is actually very easy at this point. So the midpoints for each of the intervals are pi over 8, 3 pi over 8, 5 pi over 8, 7 pi over 8. The area is going to be the sum as I goes from 1 to n of the FCIs times delta x's. Okay, the delta x is pi over 4, right? Because that's the distance from here to here. It's pi over 4. So you look, here's pi over 4. It's hard to read this. However, the resolution's not very good. Okay, so the delta x is pi over 4, and then the f of ci is just the sine of the ci's. So we're going to plug in here pi over 8, 3 pi over 8, 5 pi over 8. 7 pi over 8. I'm going to add those 4 things up. And I can just do this on my calculator. Make sure your calculator's in radians. Okay? It needs to be in radians or you're going to get the wrong answer. You're going to get about 2.052. which is approximately the area under that curve right there. Okay, so here's your assignments. 1 through 9 odd, 13 through 33 odd, 37, 45, 49, 55, 57, 61. Okay. If you have any questions, let me know. I'm happy to help you, and I will see you next time.